Hi kids, welcome back. So, what we're talking about today is isosceles triangles and equilateral triangles, and they have some very specific features that are helpful and allow you to know a lot of cool stuff. Really helpful if you know a triangle is isosceles or equilateral, it gives you a lot of information. So, here's what we're looking at here. It says the angles and sides of isosceles and equilateral triangles have a special relationship. Now, you need to know what isosceles and equilateral means. The other option would be scalene. Scalene is a triangle that has three different side measures and three different angle measures. Okay. Um, Isosceles triangles have two sides the same and therefore two base angles the same. We'll get to that in a second. And equilateral triangles have all three sides the same and therefore all three angles the same. And that is something really specific. You can always know the number of them, of the angles, the measure of the angles. So isosceles triangles are common in the real world. You can frequently see them in structures such as bridges and buildings, as well as in art and design. The congruent sides of the isosceles triangle are its legs. Remember, in an isosceles triangle, two sides are congruent. We call those the legs. Okay, and uh, the third side is the base. It might not always be sitting on this side. You might get a drawing, let's say, that, look it down here on the bottom, like looks like this, and you are told, well, basically you're told by the segment marks that this is an isosceles triangle. So then this would be the base, even though it's not sitting on it, right? It's always just the side that's not equal to the other two sides, just to be clear on that. Anyway, um, so we've got the legs and the base for the names of the sides, and the two congruent legs form the vertex angle. So that angle that separates the two equal legs is called the vertex angle, okay? And the other two angles are the base angles, and the fun phenomenon of that, which this is what it says here, the isosceles triangle theorem, that if two sides of the triangle are congruent, then the angles opposite the sides are also congruent. The angles are congruent then. So here's the two sides. Opposite angle means the angle that does not have that side as one of its uh, two rays or segments, okay? So opposite that is that, opposite that is that. If the sides are the same, then the opposite angles are, base angles are the same. And we're gonna go on this. That's a big chunk of the information you need to know, so hopefully that made sense. All right, so if we wanted to do a proof of this to be sure that the isosceles triangle theorem works, or the way that they were able to prove that it works, is this. First, we need an auxiliary line, okay, which means we're going to add another line here. And this specific line, we start out, we know that it's isosceles because it gives us these marks, okay, and segment or side xy is congruent to segment or side xc. Now, we're going to draw a bisector of the angles. We know that this angle and this angle measure the same. We're going to do it in such a way that we know that we get the same here, okay? Draw the bisector, and then essentially what you get here is this. We want to prove that this is congruent to this. The base angles are congruent. That's what it's asking us to prove, okay? Because that's what it claims, is that if you have the two congruent legs, then the base angles are congruent. Well, check out what's going on here then. If that's true, then we have a side congruent. We have the angle that's included between that side and this reflexively congruent side are congruent. So we've got two sides congruent and the included angle congruent between them. So we have side, angle, side congruence between this triangle and this triangle, and therefore that means that every part is congruent, which means that this base angle is congruent to this base angle. It also actually means that this side from y to b is congruent to this side from z to b, which means that when you drop this angle bisector down, you actually bisect that opposite side. And of course, this is a straight angle, and since these are the same, since we've identified through side angle side that the triangles are congruent, we know that these must be the same angle here, and since they are a linear pair, they must sum to 180, so they must each be 90. So this is a perpendicular bisector of this side. Neat. You know a lot of stuff there. But the fact is essentially just that we've proven that the base angles are congruent if you know the triangle is isosceles. And the converse of that is if you know the base angles are congruent, then we also know the sides opposite them are congruent. Okay, so that's the converse of that. Cool. We were learning a lot real fast. So this is a neat problem. First of all, they're giving us this particular illustration of a triangle, and here this big triangle, triangle ABC, you can see that its base angles are congruent here and here. Okay, so is segment or side AB congruent to segment or side CB? Well, if the base angles are congruent by the converse of the isosceles triangle theorem, we know that the opposite sides are congruent. So we do know that side AB is congruent to side CB. Yep, because of the converse of the isosceles triangle theorem. Now, is angle A, right here, congruent to angle DEA right here? In fact, it is, because remember, the isosceles triangle theorem says that if you have two sides in a triangle congruent, their opposite base angles are congruent. So this angle here and this angle here must be congruent. Yep, pretty cool. Here's a got it problem for you. See how you do. Okay, so I don't have access to the book answers, so what I'm going to do here is just talk you through this answer. Is angle WVS that's marked with a single angle mark, congruent to angle S, which is right here? And yes, the isosceles triangle theorem states that if the two sides of this small triangle, WVS, if two sides are congruent, their base angles are congruent as well. So this must be congruent to this. So that first answer is yes. Here is side TR congruent to side TS. Well, we have just established that this angle with a single mark is congruent to this angle, so we can also put a single angle mark there. And why don't I put it? And as you can see, then this angle here and this angle both have a single angle mark, and that means that their opposite sides are congruent. So side TR is congruent to side TS. We need to first establish that that angle was congruent to this angle and deserved to have a single angle mark as well, which means it's congruent to any other angle that has a single angle mark. Okay? Can you conclude that triangle RUV is isosceles? Triangle RUV is isosceles. Let's see. Well, my best guess is that we don't have enough information actually, because see where this side UV is? We don't have any reason to believe that it's at any particular angle. It could be coming like this. Whoops. Could be coming like this. Right? In which case that would change what this angle and this angle was. And there's no reason for this side to be locked in that particular position. So I'm going to say, no, we cannot conclude that triangle RUV is congruent because we don't know anything about this angle, and there's no reason to say that this line couldn't move with the things that we know that have to be true. Okay? Yeah, hope that makes sense. So I had stated this earlier, that if a line bisects the vertex angle of an isosceles triangle, remember the vertex angle is this top angle between the two sides that are congruent. If we draw an angle bisector down, then this line that we drew is called a perpendicular bisector to the base. It's going to be at 90-degree angles, and it's going to split that side into two equal parts. And remember what I said here is that if you draw this line down here so that these angles are the same, what you get is side angle side congruence, and therefore all parts are congruent. This angle is congruent to this angle, but very specifically, this side of the small right triangle is congruent to this side of the small right triangle. And since these are a linear pair and they must be equal since they are corresponding parts of two congruent triangles, then they must be equal in measure, and they have to sum to 180, so they have to be 90, which means they're perpendicular. Yep. Okay. Okay. I'm sorry if the sound isn't so good. I have a different set of headphones right now. Now, what is the value of x? Whoops. What is the value of x right here? Well, I have one way of doing it, and I'm just going to tell you this, that if this large triangle, triangle ABC, is isosceles, and this angle A is 54, this is 54 as well. And that means 54 and 54 is 108. And so whatever's left, it turns out is 72. When you do 180 minus this 108 for these two angles here, 72 has to be split up equally since this is bisected, and you get 36 and 36. Okay, but the way they did it here is this. Okay, they said, well, since this bisects it, we know that this is 90. So we've got 54 plus 90 plus whatever angle that is. And that's what they do here, and they still get 36. You can either do it by looking at one triangle and saying, I know that's 54, and since this is perpendicular, these two lines are perpendicular, that's 90, so what's left in the third angle? Or you can also think of it this way as well, which is that that's 54, so the large angle here, ABC, is 72, and it's bisected, so each part is 36. Okay? Suppose that measure of angle A was 27. What would be the value of x? Okay, try and figure it out right now. Okay, so then suppose that the measure of angle A is 27 and not 54. What if that was 27 instead? Well, that would be 27, so this is 27. This is a 90-degree angle, and so is that a 90-degree angle. And then so we can say we've got a 27-degree angle, a 90-degree angle, and x, and those three have to sum to 180. So we can say then 27 plus 90 plus x equals 180, or 117 plus x equals 180. And subtracting 117 from both sides, I get x is equal to 63 degrees, which is the answer they were looking for. All right, now a corollary to theorem 4-3 has to do with equilateral triangles. Now, a corollary, is a theorem that can be proved easily using another theorem. Okay, since corollary is a theorem, you can use it as reasoning. Okay, and you say, okay, if this triangle is equilateral, well, let's just say if it's equilateral, then we certainly know that it's like we have these two sides congruent, right? In which case, that would mean that we would have base angles congruent right there and there. And then we could just rotate it and say, okay, well then what if this side and this side were the isosceles triangle? It would have base angles here and here congruent, and therefore that would also have to be the same. So what we get in an equilateral triangle is all three angles are the same. And it says, if all three sides are equal measure, then all three angles are equal. Okay, and the corollary to that is if the angles are equal, the corollary to the converse of the isosceles triangle theorem is that if you have three angles congruent, then the sides must also be congruent. Okay, so in an equilateral triangle, lateral means side, so equal sides, it's equiangular as well. And if it's equiangular, equal angles, then it's equilateral or equal sides as well. So then, what are the measures of angle A, angle B, and angle ADC? Here's angle A, here's angle B, and here's angle ADC. Okay? Well, this is one angle of an equilateral triangle, and fun fact, if they're all three the same and three angles have to add up to 180, then they must add up to 60 each. And in fact, in equilateral triangles, every angle is always 60. So this is 60, which also, for the same reasoning, makes angle B 60. Now, angle ADC is really, the angle addition theorem states that this angle, 60, plus this angle, 60, will equal the large angle ADC, so therefore 120. Okay? So try this got it problem. Suppose the triangles in problem 3 are simply isosceles, and ADE and DEC, this angle here, and ECB, this angle up here, sorry if you can't see it, are vertex angles, meaning these two base angles are the same, these two base angles are the same, these two base angles are the same. And the vertex angles have a measure of 58. What is the measure of A and the measure of BCD? Calculate that now. So if for triangle ADE, we have angle A measuring, the vertex angle ADE measuring 58, then we've got angle A and angle E are the same, so we've got angle A plus angle E plus 58 equals 180. And since angle A and angle E are the same, we could substitute and say angle A plus angle A. They're equal measure, plus 58 equals 180. And what that means is then 2 times angle A plus 58 equals 180. And when we subtract away 58, we get twice angle A is equal to 122. And when you divide by 2, you get angle A is equal to 61 degrees. Okay? What about the measure of angle BCD? And that is BCD right here. We've got a vertex angle added with a base angle. And so we know the vertex angle is 58 and the base angle is 61. So what is 58 plus 61? Equals 119. So the measure of angle BCD is 119, and I should have the measure of for all of those, right? The measure of, etc. Sorry about that. Okay, there you go. Okay, so here are your lesson check problems. I need to embed the answers. I don't have access to the textbook right now. I don't know if it's the change in the year. It's kicked me out. So I will update the video and I will repost it. But for now, you have the lesson check problems that you can try, and I will give you updated video with the answers hopefully later today. And that's it. Good luck. See how you do.